Hello and welcome back to the Deep Dive. Today we're opening up Unit 8 from Class 12 Chemistry.
That's aldehydes, ketones, and carboxylic acids.
It is. But, we're not going to try and swallow the entire chapter in one go. That's just a recipe for a headache.
A very bad one.
Instead, we're zooming in on one very specific section. It looks small in the textbook, but it's actually a bit of a minefield for students during exams.
I know which one you mean.
We're talking about the physical properties of carboxylic acids.
Yes. It's a fascinating topic, and you're right about it being a minefield. It's one of those sections where the data just seems to contradict the logic you learned in all the previous chapters.
Exactly. I was going through the notes, and I hit a wall almost immediately. I'm going to start with a puzzle that completely confused me. It's about boiling points.
Okay, go on.
So usually we follow what I call mass logic, right? If a molecule is heavier, it should have a higher boiling point.
That's the general rule of thumb, yes. Van der Waals forces increase with molecular mass.
Right, so I looked at this comparison. On one side, we have methyl formate. Its molecular mass is 60.
Okay.
And on the other side, we have acetic acid, the main component of vinegar. Its molecular mass is also 60.
So same mass.
Same mass. But then you look at the boiling points. Methyl formate boils at a chilly 32 degrees Celsius. I mean, on a hot summer day, that stuff would boil right in the bottle.
It would, yeah.
But acetic acid, it boils at a scorching 118 degrees Celsius. That's hotter than boiling water.
That is a massive difference.
So how can two things with the same mass behave so differently? One just flies away and the other holds on tighter than water. The mass logic completely fails here.
It does fail, and, that failure is the most important clue. It tells us that mass isn't the driver here. Something else is gluing these acetic acid molecules together with some kind of incredible force.
Okay, sticky molecules, I get that. But before we get into the mechanics of it, why should we care? I mean, apart from the board exam, does this really matter in the real world?
Oh, it matters immensely. Understanding this stickiness is the key. It explains everything from why vinegar stays liquid in your kitchen to how pharmaceutical companies actually design medicines.
Really?
Absolutely. If these acids didn't have these specific properties, the chemical industry and even biological life would look very, very different.
Okay, let's unpack this then. If I'm a student, what's the zero-level explanation? What makes them so sticky?
At the simplest level, the answer is one thing: hydrogen bonding.
Okay, I have to stop you there because this was where I get a bit skeptical. We just studied alcohols in the previous unit, right?
Right.
Alcohols have hydrogen bonding too.
Yeah.
Ethanol has an OH group. Acetic acid has an OH group.
Yeah.
So why is the acid so much stronger? Why does it beat alcohol so badly in the boiling point race?
That is the million-dollar question, and the answer lies in the structure of the entire AsCOH group. It's not just an OH group. Think of it as a double threat.
A double threat. How so?
Well, look at the structure. You have a carbonyl group. That's the carbon double bonded to an oxygen CO, and attached to that same carbon, you have the hydroxyl group, the OH.
Okay, I'm visualizing it. C double bond O,
Right.
single bond OH.
Now, that carbonyl oxygen is very electronegative. It's pulling electrons towards itself. And because of that, the oxygen in the OH group becomes a bit electron deficient.
I see.
So what does it do? It pulls electrons even harder from its own poor hydrogen atom.
So the hydrogen in the OH group becomes even more positive than it normally would be in, say, an alcohol.
Exactly. It becomes, you could say, supercharged. This makes it a much more powerful hydrogen bond donor.
And the carbonyl oxygen, the CO part, that would be the acceptor.
Precisely. It's rich in electrons. So the molecule has a supercharged positive handle, the H, and a supercharged negative handle, the CO. It can do both things at once.
So it's not just one connection.
It's the ability to form a whole network. It can both give and take a hydrogen bond very effectively.
This is where that analogy of social molecules comes in, right?
Yeah. It's a perfect analogy. Think of carboxylic acids as highly social people. In a liquid, they form this tight-knit community. They're all holding hands.
A 3D network of connections.
A huge 3D network. To get them to boil, to escape the liquid, you have to break all those friendships, and that takes a lot of energy, a lot of heat.
Okay, but then what about aldehydes and ketones? They also have the CO group. Why aren't their boiling points as high?
They are just acquaintances. They have the negative handle, the CO, but they lack the positive one. They don't have the OH group.
So they can't offer a handshake back.
Exactly. They have dipole interactions, which is like a polite nod across the room. It's an attraction, sure, but it's very weak compared to the tight handshake of a hydrogen bond.
So that makes the hierarchy really clear. Hydrocarbons are the weakest. Aldehydes and ketones are in the middle. Alcohols are strong, and carboxylic acids are the strongest of them all.
That is the perfect order to remember for the exams.
Let's try and visualize this. I call this the mental movie. It helps to see what the molecules are doing.
Visualizing is always better than just memorizing facts.
Okay, so scene 1, we're looking at pure liquid acetic acid. If we could zoom in, what would we see?
You'd see that 3D spider web. Every OH from one molecule is pointing to a CO of a neighboring molecule. It's a crowded, connected network.
And that's why you need 118 degrees Celsius. You're not just lifting one molecule, you're trying to rip the whole web apart.
Precisely.
Okay, scene 2. Now we pour some water into this beaker. What happens?
The social acid molecules are happy. Water is also an expert at hydrogen bonding, so the acid molecules will gladly break some of their own connections to form new ones with water.
They integrate into the water's own network.
Perfectly. The CO of the acid grabs a water hydrogen. The OH of the acid grabs a water oxygen. They mix very, very well.
So they are highly soluble?
The lower ones, yes. Up to 4 carbons, they are completely miscible with water.
But there's a catch, isn't there? The carbon chain length.
Yes, the tail. The SaCOH group is the head. It's hydrophilic. It loves water. But the hydrocarbon chain attached to it is the tail.
And that's hydrophobic. Oily. It hates water.
Exactly. So as that tail gets longer and longer, say from acetic acid with 2 carbons to something like stearic acid with 18,
the tail starts to win.
the hydrophobic part wins. The molecule becomes much less soluble in water.
Okay, that makes sense. Small acid, soluble. Big acid, insoluble.
That's the rule.
Now for scene 3, this is the plot twist. This is the one that always shows up in the tricky part of the exam paper. We take our acetic acid, but instead of water, we dissolve it in benzene.
Ah, benzene, a non-polar solvent. It's, you could say, antisocial.
Right. It doesn't do H bonds.
Duh.
So the acid molecules were suddenly in this environment where nobody wants to interact with them. What do?
They do something very clever. They find each other. 2 acetic acid molecules will find one another in that sea of benzene and pair up.
A pair?
Yes, and they form a very specific, stable structure. It's called a dimer. Di for 2.
How does that work?
Imagine 2 molecules face to face. Molecule A uses its carbonyl oxygen to grab the hydrogen from molecule B's hydroxyl group. And at the very same time, molecule B uses its carbonyl oxygen to grab the hydrogen from molecule A.
It's a closed loop. They're holding each other in a circle.
An 8-membered ring held together by 2 hydrogen bonds. It is incredibly stable. They float through the benzene as these little couples.
So if you were to measure the molecular mass in that solution, you wouldn't see particles of mass 60. You'd see particles of mass 120.
Yes. And that is the ultimate exam trap. It connects to the solutions chapter. If you try to calculate the molar mass of acetic acid in benzene, you will get an answer of 120, not 60.
And if you don't explain why, you lose the marks.
The key word is association. You must say the molecules associate to form a dimer.
Now, does this dimer thing only happen in benzene?
This is the really fascinating part. Those 2 hydrogen bonds are so strong that they even exist in the vapor phase.
Wait, you mean even when it's a gas?
Yes. When you boil acetic acid, some of the molecules that escape into the gas are still holding hands in that dimer form.
That's incredible.
Yeah.
We always think of gas particles as being completely separate and flying around alone.
But not always these ones. It just shows you how powerful that double hydrogen bond lock really is.
Let's bring this back to a real-world application. You mentioned pharmaceuticals earlier.
Yes, this is very important in what's called crystal engineering.
Sounds complicated.
It is, but the idea is simple. When a company makes a pill, say, for a headache, they need to turn the drug chemical into a solid crystal.
Okay.
The way those molecules stack together in the crystal, which is controlled by their sticky ends, like hydrogen bonds, determines how fast the pill dissolves in your stomach.
So if the packing is wrong, the medicine might not work properly.
It might not dissolve at all. So chemists use their understanding of dimerization and hydrogen bonding to, well, engineer the perfect crystal, one that dissolves at just the right rate.
So they're literally using these sticky ends to make sure a medicine works.
It's molecular architecture, really.
That is a brilliant connection.
Yeah.
Okay, we're coming towards the end, and I want to arm our listeners for their exams. Let's do the cheat codes.
The clarity lines. The sentences the examiner is looking for.
Perfect. Scenario 1. The question asks, why do carboxylic acids have higher boiling points than alcohols of comparable mass?
Okay, your answer needs 2 points for full marks. First, Carboxylic acids form more extensive intermolecular hydrogen bonds than alcohol.
More extensive.
Yes, and second, this is because each molecule can both donate and accept a hydrogen bond, leading to strong molecular association. Don't just say each bonding, you must mention the extent or the network.
Got it. Okay, scenario 2. Why are lower carboxylic acids soluble in water?
The line is, because they can form hydrogen bonds with water molecules. But for the extra mark, you must add the condition.
The tail.
The tail, add. However, solubility decreases as the size of the hydrophobic alkyl group increases. That shows you understand the whole picture.
Brilliant. Scenario 3, the big one. Explain the anomalous molecular mass of ethanoic acid in benzene.
You must use the word dimer. The line is, in nonpolar solvents like benzene, carboxylic acid molecules undergo association to form a stable cyclic dimer through two intermolecular hydrogen bonds.
And you said to draw it.
Absolutely. A quick drawing of the dimer structure is worth full marks, instantly.
Fantastic. Last one, scenario 4. Why is the OH bond in a carboxylic acid more polarized than in an alcohol?
This goes back to the beginning. The answer is, this is due to the electron withdrawing effect of the adjacent carbonyl group, which increases the polarity of the OH bond.
That sounds like a topper's answer.
It is. It shows you understand the underlying electronics.
So, to wrap this all up, we started with this puzzle. A molecule with the same mass as another, but a boiling point that was almost 90 degrees higher.
And we found the answer wasn't in the mass, but in the connections, the social network.
The network makes the liquid strong, and it takes a huge amount of energy to break it.
And even when you put them in an antisocial environment like benzene, they just pair up to survive.
I want to leave everyone with a final thought. Next time you're in the kitchen and you smell vinegar,
Which is just a dilute solution of acetic acid.
remember what's actually happening. For you to smell it, those molecules had to escape from that sticky liquid web.
They had to break free.
But because those connections are so strong, even in the air flying up into your nose, some of them are likely still holding hands.
You're actually inhaling microscopic dimers.
Exactly. You are smelling tiny couples that refuse to let go. That, right there, is the power of the hydrogen bond.
It's an invisible force, but strong enough to defy even the transition to a gas.
On that note, good luck with Unit 8. Visualize that network, visualize the dimers, and those exam questions should feel a lot easier.
Happy studying, everyone.
Thanks for listening to this deep dive. We'll catch you in the next one.